Okay, so this is the outline of this chapter. So first, we will talk about the simultaneity, 同时性, and then the time dilation, 时间通胀, and then the relativity of length, which means that the object will have a length, but if it is in different inertial reference frame, then you will see the object with a different length. And then we'll talk about the Lorentz transformation, and then the relativity of velocity. And in the primary school, you may know that just say if Tom is running 6 meters per second in the west, and then to the west, and maybe another one John running in another speed, maybe 3 meters per second to the east. What is the relative velocity? And they may feel that 6 plus 3 is 9, but actually if the velocity of an object is fast enough, then it is not simply algebraic sum. And then we will also talk about the Doppler's effect for the light, and also the momentum and the energy, which means we will talk about the mass energy equation, the well-known E equals mc squared. Okay, so first we will talk about the two postulates for the special theory of relativity. Postulate means 假设假设或者是假说。So the first one is the relativity postulate. So it says the law of physics are the same for observer in all inertial reference frame. So inertia is very important here. So no one frame is preferred over any other. So what is inertial reference frame? In Chinese, this is called 惯性坐标系。惯性reference frame 坐标系嘛。惯性 means it moves in a constant velocity. The velocity doesn't change. Maybe it can just still there, but maybe or maybe it can move in a direction in a constant speed. Okay, so this is called the inertial reference frame. So the special relativity mostly based on the inertial reference frame. Okay, and then the second postulate is that the speed of light postulate. The speed of light in vacuum has the same value c in all directions and in all inertial reference frames. So this is interesting. This is actually contradict our insight or our thinking. Yes, actually. So just now I mentioned that if one is moving 6 meters per second towards another one moving 3 meters per second towards each other. If this is B, then A may feel that B is moving 9 meters per second towards him. But here it says that the speed of light is always c. If you are wanting towards the light, maybe v, maybe 100 meters per second, then you still, c is still that c, 2.998 times 10 to the 8th power. If you are moving away from it, it is still the same. If you are moving maybe 1/10 of the c, maybe it is 1/10 of the c. If you still use the intuitive sense, you may feel that it is 11/10 c go towards you, but actually not. C is still c. It doesn't change, even though you are moving towards it, moving away from it. This is a very important postulate here, which is out of the imagination, based on the classical physics. Actually, you may say why it make this postulate. Actually, it's based on the experiment. Actually, at that time, the scientists or the physician believe that in the space there are something called the ether to transmit the EM wave, transmit the light. and they are very willing to find this ether to find, oh, it should be some ether to transmit the light, something like the voice. In the voice, we need the air or some other material to transmit the voice. If it is in a vacuum, then you cannot hear the sound if without any material, because it needs some oscillation to transmit the wave. But for the speed of light, it seems that it can also transmit in the vacuum. So that's the problem. Why? Then the physician at that time believed that there should be something called the ether to transmit the EM wave of the light. So yeah, and of course there are some experiments imply this one to happen. One is that the physician try to accelerate the particle. So actually the particle can never reach the ultimate speed, which is the speed of light, which is 2.998 times 10 to the 8th power here. It tried to increase the energy of the particle, but it can never reach, because according to the classical mechanics, we know that K equals half of mv squared, which means that even though this is a square, but if you increase this kinetic energy, then the velocity should be greater than the speed of light at some point. You can just plug in the value. If you plug in c to be 2.998 times 10 to the 8th power meter per second, and then for the particle, maybe the lightest particle might be the electron, 9.11 times 10 to the minus 31 kilogram. Plug in the value, you know what should be the kinetic energy to reach the speed of light. But actually, the particle can never reach exactly the speed of light. So this is one of the experiment implying that. Another one is called the most famous failed experiment, called the Mikosan experiment. But actually, I have skipped the chapter 35, so I just remark it quickly. So this is so-called the Mikosan Interferometer. 就是 Mikosan 就是名字嘛 ，Interferometer 是叫做干涉仪啊，干涉仪。So this is the interferometer. So you can see there is a source here, transmits some of the light in two directions. So this is a splitter. So it will split the light in two directions. One of it go to this way, and then one of it go to another way. The distance between this mirror and the splitter, and this mirror and this splitter, should be the same. D1, D2 should be the same, which means that the time it takes to the light to travel should be the same. However, actually on the Earth, the Earth is moving, is rotating, and then also rotating around the sun, you know. So in this sense, there must be some velocity adding towards the speed of light. So it should measure that considering the speed of the Earth, then the time it takes the time it takes to travel this path and this path should be different. And then finally, the light here will combine here, and then here we can measure the light. And of course, actually, it is not using this one, the telescope to measure. Actually, it has something called the inference, 干涉. So which means that if we have if you remember, I think in high school you have learned something called the double slit. The double slit, maybe I draw it in another page. In high school, you should have learned something called the double slit interference, 双狭缝干涉. So which means that if you have some source, some light source from here, and then you have a two slit, then you will see there will be something light and dark, and then the pattern is called the double slit interference. So we find that there is the double slit interference, and actually according to this experiment, it found that the speed of light in two directions are actually the same. It doesn't influenced by the speed of the Earth, even though it might be quite slow compared to the speed of light. But actually, if you use the light to measure the distance, it should be very accurate. So this is so-called the most famous failed experiment. Mikosan is related to the interferometer, and then of course Morley joined this experiment, and then original objective of this experiment is to prove the existence of the ether. Just now I mentioned the ether. The physician believed that there should be some ether for the propagation of the EM wave of the light, but actually failed, because if ether exists, then the speed of light in two directions should be different. But here you find that the speed of light in the two directions are actually the same. So the conclusion of this experiment is that the speed of light is a constant for different inertial reference frame. And due to these two types of experiment, they try to come up with this postulate that the speed of light should be constant no matter what is your inertial reference frame, even though you're moving fast, even though you're moving half of the speed of light towards or away from the light, then the speed of light is still c. Okay, so if you are interested, you can check this link about the Mikosan-Morley experiment. Okay, so next we talk about the simultaneity, 同时性. And then also the time dilation. Okay, so this means that the time is relative. The time is not absolute. Originally, we may think that the time for different objects should be the same, but actually not. If you are moving faster, then your clock will moving slower. Yeah, that's very interesting. And so here it says an event is something that happened, and every event can be assigned three space coordinate. So XYZ, the three space coordinate, and one time coordinate, the time t. And then among many possible event are one, turning on or off the tiny light bulb. So turning on a light bulb, and then the collision of two particles, the sweeping hand of a clock plus a marker on the river clock. So if two observers are in relative motion, they will not in general agree as to whether the two events are simultaneous. So how we define the simultaneity is that we use the speed of light, because, for example, if Sally is here, Sam is here, and there is a event occurs here, and then there is another event red occurred here, and you assume that this is a rocket which is very, very long. It takes maybe a few seconds for the speed of light, for the light to travel. So how do we determine whether this one occur first and this one occur first in their reference frame? If here Sally is moving to the right side, so if Sally is moving to the right side, V, and then it will, and when B happen and R happen, just imagine at the same time, but yeah, at the same time, but Sally is moving to the right side. So when this happens, it will transmit some light in any direction. So if Sally is moving to the right side, Sally will detect this red light first, and then the blue light is still propagating in here, and then sometimes later the red light and the blue light will approach the SAM in the middle, because SAM doesn't really move. So SAM will feel that blue and red occurs at the same time, because it receives the blue light and the red light at the same time. However, sometimes later, Sally moves to here, and then she sends the blue light. So Sally may feel that red occur first. So here it says simultaneity is not an absolute concept. It's not absolute concept. For Sam, it feels that it occurs at the same time. But for Sally, it feels that the event red occur first. So it's not absolute concept, but rather a relative one, depending on the motion of the observer. So we really need to consider the velocity and the position of the observer to say that whether a event occurs first. Okay, so if the relative speed of the observer is much less than the speed of light, then measure departure of the simultaneity are so small that are not noticeable, because for the classical physics, all the things move very slow. So for the speed of light, it is much faster than any velocity we are concerning. So it doesn't really matter. So in this case, all our experiment of daily life, that is why the relativity simultaneity is unfamiliar, because we seldomly face this type of event, which is a very large scale and or moving very fast. Okay, so just mention what I've mentioned. Okay, so this is a simultaneity, and then we talk about the time dilation, 时间膨胀. Okay, so here you can see the time interval between two events depends on how far apart they occur. Both space and time, that is their spatial and temporal separation. 空间跟时间的分隔 are entangled. Okay, so here, if this object is here, and there is a mirror, the distance between them is capital D. So it tries to transmit the light towards the mirror and then reflect. So it can measure the time it takes the light takes to travel for this path, 2D. Okay, so it measured the time to be delta t0, and then the next experiment is that if B is moving to the right side with a velocity v, which is comparative to the speed of light. Okay, so here it moves to here. It takes delta t to move to here. Also, it transmits the light towards the mirror and then reflected back. So this is still d, but it moves for this distance. So this is a right angle triangle. So you use the Pythagorean theorem to see that L is actually d squared plus half of v delta t squared, like this. Okay, so the deal here is that delta t0 and delta t will be different. Actually, for this b, it does not move. It will still the speed of light to be c. But for this one, this b is moving, which means that if it moves to here, the light travel to this point, it will still, which I mean this observer will still feel that the speed of light is moving with a constant velocity c, which means that it is something like it moves in this direction with a speed of light c. Okay, it says if two successive events occur at the same place in an inertial reference frame, the time interval delta t0 between them measured on a single clock where they occur. So it used a single clock to measure this one, because you can just put this clock at this point to measure the time of the light start to transmit and the receive at this point. But here it needs two clocks. One clock here, it try to transmit the light towards the mirror, and then the clock should be placed here to measure the time it takes to receive the light coming back. So observer in frame moving relative to the frame such that the observer on the clock on the track watch Sally and her experiment move past will always measure a larger value, delta t, for the time interval. So delta t always larger than the proper time. This is so-called the proper time delta t0 for a single reference frame without moving. You use a single clock to measure the time. It is so-called the proper time. And this one is the time measured by two clock for the object moving on that clock. And effect is known as the time dilation. 所以就时间膨胀嘛，这个就是比那个大。How do we derive this equation? Actually, the time dilation will follow this equation. Actually, here we have d equals here we have d equals maybe I use a thinner one. Yeah. D equals c delta t0 over 2, because it takes time to travel 2d, 1d and another d. So 2d over c, this is a distance over the speed of light, will be the proper time. So we have a delta t0 equals 2d over c. So we have d equals this one. And also for this one, here we have L squared equals d squared plus half of v delta t quantity squared. So this is half of V delta T, and this is D. So according to Pythagorean theorem, we have this expression. And also here we have L equals C delta T over 2, because it takes 2L. It takes time delta T to travel 2L. With this time, dilated time. Okay, so yeah, it takes time delta T to travel this distance. Okay, so in this sense, you can just plug in this one and this one into here. So we have C delta T all over 2 square equals D square is C delta T0 over 2 quantity square plus V delta T over 2 quantity square. So all the C square, not all the C square, all the 2 will be cancelled. Only all the 2 will be cancelled. 2 will be cancelled. All the 2 square will be cancelled. And then you can move this term to the left side. So we have a C square and then delta T square minus delta. No, I should not move this term over. I should move this term over. So that we can factor out delta T square. So it will be like C square minus V square, and then multiplied by delta T square equals this one, C square times delta T0 square, like this. Okay, so finally we divide C square minus V square on both sides. So we will have delta T square equals C square over C square minus V square, and then delta T 0 square. And then we take the square root on both sides. So we have delta T equals delta T0 over this term. We can just divide C square on both the denominator and in the denominator and the numerator, so that it becomes 1 over 1 minus these. We still have the square there. So here will be 1 over V square over C square delta T0 square. So we take the square root on both sides, so it becomes 1 over square root of this term, 1 over square root of 1 minus V over C quantity square, like this. So this is the equation of the time dilation. And sometimes we will use beta to stand for V over C, which is the portion of the speed compared to the speed of light. So beta is always less than 1, less than or equal to maybe, or larger than 0, something like that. Should be 0. Okay, and also we can use the gamma to stand for 1 over square root of 1 minus beta square, meaning the whole term. So it makes the equation very compact, like delta T equals gamma times delta T0. And of course, 1 minus beta square is, and then take the square root, is always less than 1. So 1 over this term is always larger than 1. So we have a gamma always larger or equal to 1. When beta is 0, which means that V equals 0, beta is 0, then 1 minus 0, take the square root, is 1, 1 over 1 is 1. So when V is 0, gamma equals 1, If v is larger than 0, then this one will be larger than 1. If v is closer and closer to the speed of light, which means that b is approaching 1, b is approaching 1, then 1 minus this beta square will be a small number, and take the square will still be a small number, and then gamma will become very large. That's the time dilation. Even though gamma is small, and it is still the time dilation. But usually, if we really need to feel the time dilation, then the speed should be close to the speed of light, and the gamma is called the Lorentz factor. Okay, of course, v over c, it does not have any SI unit, because this is a speed, this is another speed, so they cancel each other. Beta is a dimensionless variable, and so as this one. This is dimensionless. 1 minus dimensionless is still dimensionless. So gamma is still dimensionless factor. So this is time, this is time, this is dimensionless. Okay. Oh, actually, this is the derivation here. So actually, this one is like delta t0 equals 2d over c, and then delta t equals 2l over c, and then we make use of the Pythagorean theorem. We get this one, and then we plug in this one here and this one here, so that we will get the equation of time dilation. Okay, so let us see a sample problem so that we can know how to use it. So it says your starship pass Earth with a relative speed of 0.9990 c, so very close to the speed of light. After traveling 10 years, your time means on the starship, you stop at lookout post LP13, turn and then travel back to Earth with the same relative speed. The trip back takes another 10 years, of course. So also your time. So how long does the round trip take according to the measurement made on Earth? So this is very interesting, which is so-called the twin paradox, 双生子仰谬. Okay, so negate any effect due to the acceleration involved with stopping, turning, and getting back up to the speed. Okay, so this is just the time dilation. So delta t is nothing but delta t0 over 1 over v over c quantity squared. So it takes you 10 years for a single trip. So, and then 1 minus 0.999 and then square like this. So it takes 223.7 years. So even though it takes you 10 years on the starship to travel from Earth to that post, and then on the Earth, actually, it passed 223.7 years. And then the delta t round trip is actually 2 times delta t, which is 447.3 years. Actually, this number is not very good design bit. If you just make this velocity smaller, then you can say a story that there is a train on the Earth, and then one of it travel on a starship towards another planet with a speed which is lower. Then it takes 10 years, or maybe it takes 1 year for the train for one of the train to travel to the star and to the planet, and then going back takes another year. So the one who takes the trip only past 2 years, but after he go back to the Earth, he will find that the twin already become an old man. It takes maybe a few decades. So this is the so-called the twin paradox, and actually there is no problem for the special relativity. It will be the case. It will be the case. If you are interested, you can check the link about the twin paradox there. It may tell you more. And this is another one. It says the elementary particle known as the positive kaon, K plus, is unstable in that it can decay into other particle. Also, the decay occurs randomly. We find that on average, a positive kaon has a lifetime 0.123 millisecond when stationary. That is when the lifetime is measured in the rest reference frame of the kaon. So if a positive kaon has a speed 0.990 c relative to the lab reference frame when the kaon is produced, how far it can travel in the frame during the lifetime according to the classical physics, which is reasonable approximation for the speed much less than c. And according to the special relativity, what is the correct for the physical possible speed? So for first one is the classical physics, or CP, classical physics. So which is V delta t. Distance equals velocity times the time. So it is 0.990 times 2.998 times 10 to the 8th power. So this is the speed, and then times 0.1237 times 10 to minus 6. So this is the time. So it takes, the distance will be 36.7 meters. So this is the value calculated by the classical physics. And then the second one for the special relativity. So V delta t, it is V delta t. But delta t is actually the dilated time. So it will be V delta t0 over 1 over square root of V square over C square, or V over C quantity square. So this is nothing but still this one 0.990 times 2.998 times 10 to the 8th power. This is the speed of the speed, and then times the proper time. Proper time is 0.1237 times 10 to the minus 6, and then square root of 1 minus 0.990 c over c quantity square, like this. So yeah, so it is 258.7 meter. Okay, so the distance will be quite different, and of course the correct one should be the second one, the correct one. This one is correct. This one will be underestimate. This one will underestimate the distance. Okay. So let us stop here today, and I'll see you tomorrow.